Hello everyone, I'm Ettore, and today I'm going to interview the WARR team from the TUM University. Could you please introduce yourselves?
Us the opportunity to join this interview and for organizing everything. My name is Greta and I am from the PR team. Yes, looking forward for this interview.
My name is Bernhard. I'm the lead of the electronics team.
Yeah, hi, I'm Lewis. I'm the current project leader of Project NIXUS. I hope we can have a few interesting discussions with you, and I hand over to Matthias.
Yeah, my name is Matthias. Unfortunately, we didn't have the chance to meet at EuRoC, but I'm now the head of rocketry, and we will have a fruitful exchange, I guess, and I will hand over to our last participant today.
My name is Max, and I'm leading the propulsion team in Project NIXUS from WARR Rocketry.
How did the WARR team start and then grow?
WARR, as a team, as an association, is situated at the Technical University of Munich for more than 60 years already. So we founded ourselves in 1962. And a bunch of students back then decided to start dive into the development of student rockets, smaller rockets, and especially hybrids, which was a first for Germany. So that was basically how the association and everything was founded by then. And in the meantime, we've grown a lot actually. So right now, the WARR itself is not just only rocketry anymore. We have a bunch of other subteams as well, namely 4. So we have the rocketry team. All of us are a part of that one right now, and we're going to talk a lot about rocketry today, but I just want to briefly mention the other ones that we have as well. So we have WARR Move, which is a team that dives deep into satellite technology and satellite development. They have a bunch of CubeSats in orbit right now, actually, and also quite some achievements on their agenda. Then there is WARR Space Robotics. They deal with robotics application in space. So, for example, autonomous rovers, but also interesting future concepts like a space elevator. And then lastly, we have WARR Space Labs, which is a team that does experiments in microgravity. So they, for example, participated in a competition of the DLR, which was called the Überfliegerwettbewerb, and they were able to send one of their microgravity experiments to the ISS with themselves. So all in all, we as WARR have quite some achievements already done in our hardware and our own development. And right now I think we are above 300 students, or just around 300 students. We're actually the biggest student group at the Technical University of Munich, and out of those 300, roughly, we are like a 150 in rocketry. So we are also the biggest team amongst the WARR itself. And I think I would just give the mic to Lewis to talk a little bit more about Project NIXUS in detail.
So specifically talking about Project NIXUS, the one that participated in EuRoC 2023. And we will participate with the same project in EuRoC 2024 as well. So what drives our development is basically, we want to be or to have a really professional development of our rockets. We aim for a bi-liquid system, and really important for us is especially the aspect of exchanging information with other students teams, and always aiming for the best possible tech we can have as a student, basically. In general, we want to contribute to the wider field of rocketry and expand in terms of getting to the industry standard technology that every space company is currently using. So we are developing a lot in bi-liquid, new tech, new space tech stuff that we want to test at competitions like EuRoC, and we are happy to contribute to the competition as well.
How's your university, TUM?
University life in general, I think we can all agree that it's pretty great. I mean, Munich itself it's a major student city because there's not just a technical university, but there's also Ludwig Maximilian and also the Hochschule München. So there are multiple universities, and that means that obviously there's many students in the city. The city itself is pretty safe, I would guess. I mean, I've never had any weird experiences, but I don't know if I can speak for everyone. And let's say maybe talking a bit more specific about TUM. Of course, it's a very challenging university. It would be a lie to say it's doable, very easy. You have to put in a lot of effort, a lot of work. But I think it's worth it in the end because it's as I said, a really good university. And of course, the other good side of TUM is that there are really nice student groups such as WARR Rocketry, which is great. Great tool to actually apply your knowledge, because let's say lectures themselves are very theoretical and they don't always give you, let's say, all of the insights that you require as an engineer. Because of course, being a good engineer means knowing your theory, having a lot of experience, and in order to have experience, you need to apply your knowledge. So that's one thing. And let's say the structure of the course itself, I think pretty much depends on what you study. I personally study aerospace engineering, bachelor's. And what I can say from my degree is the first 2 years are very tough. A lot of theory, basically only theory. And then the third year gets more engaging because you do have a lot of electives and, let's say, a bit more practical.
What are the other teams in your university?
Yeah, so we have a lot of student groups in different sectors. For example, we have a Too Fast, so they are participating in student formula racing events. We also have some drone stuff happening with both Levitum and Horizon. While Levitum is trying to build a hydrogen drone, basically Horizon is more on the side of, I think, the control theory side on things, as far as I know. And they have a really cool prototype already made and flown about. They want to bring some medical stuff to facilities and provide that. Other student groups, we also have Dash. They are working on a exoskeleton that should provide help for disabled people, basically. And I know Akaflieg, they are building their own gliders, basically, and they are flying their own gliders and can make a license in their student team. TUM Boring, so the guys participated in the Elon Musk boring competition 2 years in a row and won the competition, so we have them as well here. And TUM Hyperloop, which is also in some sort of the same competition direction as TUM Boring, so they also won the Hyperloop competition multiple times in a row. So they are quite good as well, but they transition to being more independent of these contests and are developing a full-scale prototype right now, I think. But I'm pretty sure there are some more left. So I might have forgot some.
Because actually my friend is the founder of it, so I know a little bit about it. It's called Falcon Vision, and they build drones, but I don't think they're as big as the Horizon drones. They're smaller drones, and they focus also on rescue missions, as far as I know as of now. But I think they're going to develop drones in different directions as well.
What are your job opportunities when you finish university?
Yeah, Munich or the surroundings of the city are like a pretty big technology cluster and also other stuff. So I think, or especially talking about aerospace industry and stuff like that, there's a lot going on. So there are many companies that are in the city or around the city where you can find jobs afterwards. There are both like big established companies, like for example Airbus, but then there are also plenty of smaller companies, startups, for example, like ESA Aerospace, that are working in the field of aerospace engineering, and so there's plenty of opportunities to find a job in the aerospace sector in the city of Munich or around the city of Munich later on. So I think for Germany there are basically two major clusters of aerospace industry that are located around Munich and then around Hamburg and Bremen. So yeah, our university here has pretty good contacts in this direction as well. And especially the student groups, they also try to have a close relationship with many industry partners. So there's also decent job opportunities from there. If you work together with our sponsors, for example, on a certain topic, you already have the opportunity to network and maybe try to find some working student job that you can do besides your studies if you find the time. And then for later on, I think those are like pretty good opportunities to find a job later on. So there are also a bunch of people in WARR that are doing working student jobs in many of those companies that are around the city here. So there's actually a lot you can do.
What are your team's goals and your active projects?
let's call them short-term goals. It's more like participating with Project NIXUS in EuRoC 2024. We weren't able to launch last year, but we're pretty confident that we can make it happen at this year's competition. Yeah, so we are aiming to improve our systems. We actually passed our new flight engine CDR yesterday. So we developed a new iteration of our regeneratively cooled chamber. And so we are enhancing on a lot of subsystems of the rocket currently, and want to make it more robust. And yeah, so our short-term goals basically being the first German student team that launches a bi-liquid rocket, and I think we would be also the first European team that launches a cryogenic bi-liquid rocket, because we haven't seen much cryogenic action going on in student teams so far. We are quite proud of that. Although we already launched a cryogenic system back in July with our hybrid 10 kilonewton system. We had liquid oxygen as oxidizer there as well. So yeah, this would conclude the first cryogenic bi-liquid rocket of us if we launch in October 2024. And speaking of long-term term goals, it's more like I already mentioned earlier, that we are always striving to develop the most industry standard systems. So what I'm talking about here is pump fed cycles that we want to look into, or we are already currently looking into. So to get away from the pressure fed system we are currently running, to get more to the industry standard tech, that everyone is basically using right now. This would be the short and long term goals, and we're really happy to participate next year again, or we want to participate next year again, and hopefully see the rocket fly finally.
So you want to add turbo pumps to your rocket engine?
We want to add electrical pumps, so no turbo pumps, but e-pumps. So we are currently looking into the mechanical design as well as the engine controller side, and more stuff relating e-pumps as well. So there's a lot going on. But it's currently in the first development step. So we run some preliminary or mission definition reviews and stuff like that. And first tests will follow this summer. So that's the timeline. But just prototypes this year, and in EuRoC 2025 we're aiming for a pump fed cycle in the competition.
How do you recruit new members to your team?
Recruitment is obviously a big topic because we are a student group, so people come to us during their studies, and when they are finished with their studies, they also leave again, sadly. So we always have to make sure that we have new people coming to the team, and that we can make new people have a passion for rocketry, so that they want to also apply their knowledge from universities. So what we do very actively is show ourselves around the university, around campus. So whenever there are some events or like get-togethers, then we try to actively participate. So in fairs, for example, or in other kind of displays where we can show our hardware, show what we do, and by that try to get the people into rocketry. This is something that we do very actively. Obviously also our social media presence contributes to that. So when I was thinking about where to study, I also stumbled across the website, for example, from WARR, and was like, hey, pretty cool what they are doing down there in Munich. So I decided to go. So this obviously contributes a lot as well. And then we basically do our recruitment on a semester basis. So in the beginning of every semester, we hold a bunch of recruitment events where we introduce the team and introduce new tasks and stuff that we want to achieve in that semester. And then from then on, we try to get the new people into the team, bringing them to our sub-team meetings and so on. And this aspect, I think Max can describe it pretty good, because he's actually running one of those sub-teams right now with the propulsion team.
We don't have an application process or anything like that, like we see from other teams. We basically let anyone join the team and then go from there with including them into all of the tasks and so on. So we get a lot of students every semester that join the team. We then most of the time have some issue in the beginning, because we get so many, to distribute the tasks and get them on board and start with the introduction of how we manage our tasks and so on. But then over time, it sort of clears out who really has the ambition to put in the work and also really is interested enough to keep going in the end. Yeah, I just wanted to make the point that we don't have a strict selection process. So each and everyone can join, and then we go from there.
We see ourselves as some kind of education institution besides university. So we give the students the opportunity to apply their theoretical knowledge in practical projects. So this is why we also say we are open for everyone, because they are not coming because they have like the skill set already. They are coming to us because with us they can actually learn what it means to develop a rocket or develop any other cool tech project and do applied engineering, applied sciences. So this is why we don't have any kind of selection process or don't require a certain set of skills when people come to us.
What can members learn from joining your team?
Again, in general, we don't expect any existing skills or knowledge. So you can actually learn just about anything we do. And I can just roughly line out from an electronics team perspective how we approach it, and then maybe you guys would like to add anything. But basically this year we had, for the first time, we kind of were forced to do like a really formal onboarding training for new members, because a lot of our old members, actually most of them, left. So it was like 2 people left. We had to kind of improvise. And basically what we did is, for a couple of weeks, we just did some workshops, and it was just focused on teaching members everything that we know. Some of the old members were helping with that. It took some time, but I think the investment was really worth it, because now we have a baseline and everyone has a basic amount of knowledge that they can now apply to their tasks. And of course, it takes some time to get used to tools and stuff, but I think some of the fundamentals to take care of this in the beginning makes a lot of sense in such a situation. And in terms of what type of stuff you can learn in the team, it's really the whole process. So really, I think one of the most profound things is, and that you definitely don't necessarily get taught in university, is like taking ownership of a system. Basically, and designing it to a certain set of requirements. And I think this, you can think through it in theory, but like doing it in practice is a whole different beast. And I think this is one of the only ways that you can actually learn to do this. And working in a student team like WARR is a really great way to learn this. And once you have a system designed, there's other tools that you get to use. For example, in the electronics team, you get to use PCB design tools. You get to design your circuits, design your circuit boards, assemble them. You get some manufacturing skills. We have access to really, really high-end machines that normally you would never be able to afford to use through the cooperation with Makerspace in Munich. So we have access to pick-and-place machines, soldering ovens, really fancy vapor phase stuff. And you get to learn micro soldering if you want to, and that kind of stuff. And then it translates also to the operations part, which I personally find really, really interesting as well. You get to know like how to integrate an electronic system inside of the final rocket. It's also really interesting, lots of interfaces to other teams that need to be taken care of. And it's also really valuable learning experience if you get to integration and you've neglected your interfaces, and then stuff goes wrong and you can really feel the consequences of your actions.
In my opinion, the biggest thing that you can learn at our association is that you can basically build anything if you are willing to invest the time into it, even without prior knowledge. This means putting the time in to learn the stuff and like really go deep into it. You can build anything. And this is also how we approach it in most of the sub-teams. We don't have any regular workshops or anything like that to really transfer the knowledge in like a more systematic way. Most of the time, we just assign the tasks to members that are interested in them and want to put the time into the task. And then those students can like go out and try to solve the problems that they are facing. And then if they hit a wall or don't know how to go on from any point, they can ask other members if they have recommendations on how to approach this problem. And then that solves the issue most of the time. And in extreme cases, we then, for example, have to approach chairs at the university on guidance or more technical details on how to solve the issues. But most of the time, we're able to solve it inside of the team.
I think the two most scenarios where I learned the most in WARR is, first of all, in testing scenarios. So when we test components, where we do integrated test, that's always the parts where I learn the most, because you have the whole system in front of you and you need to know how it works. You have all the members there that already know the stuff, but once they give you some sort of responsibility over a certain task, you need to, like Matthias said, or Max, I don't remember, you need to own your task. Wait, no, it was Spanner. You need to own your task, and I think that's the most important stuff, because when I was thrown in, I was back then, I got the team leader for the aerostructures team in Project Cryosphere, and this was the time where I basically learned the most, because I was just thrown into the task, and I knew if I can't finish it, we won't fly. And this is when the responsibility needs you to take action, basically, and design your system, and get help from others, of course, but also try to build it on your own or with your team. Let's put it like this. And in testing opportunities, I think it's also really valuable learning opportunities.
Could you tell me how you design your rocket?
Who should answer that? Yeah, so I think it happens on multiple stages. So this year we have the great benefit that we have a baseline version of our rocket already done, because we designed our rocket for last year, but especially for our first iteration, which is called EX4. It took a while until you find ways to develop your system. Of course, you can always take the cleanest way, like industry would, with requirements engineering and all the fancy flow charts and the whole system architecture stuff. But let's be real, we are also just students, so we might not have known from the beginning of these stuff. Although we did a quite good requirements engineering for the rocket, lots of stuff changes during the way, so you need to adapt in various scenarios, and that's what makes the process really complicated. So I think for the baseline rocket that we have right now, it took us 2 to 3 years, I would say. Now we are entering the design cycle of 1 year, and we started to implement more systematic ways to design our vehicle, going from proper systems engineering to the whole integrated system tests in the end. So we want to get more into this, and we already have our system model set up for this year, and so on. So in the future, we want to be more systematic, and then you collect a lot of prior knowledge. So where we would always start is, or where we did start this year, was basically sitting together with a lot of old and new members and thinking about, okay, what do we actually want to change in the system, and what has to stay or should stay the same for next year. So that was, I think, our first meeting we actually had this year, where we decided what we want to change in the rocket. And from that, we formulated requirements that the new system should hold, and we used a lot of old ones as well. We built a system model. Some of the teams, like electronics, for example, transmitted or transferred their knowledge through workshops first, and now they are really starting the development phase. And then we're going through a lot of design phases, where we design the whole system, subcomponents, etc. Go through preliminary design reviews. Later we go through critical design reviews, and in the end we do subsystem tests. And usually in spring or summer we do the whole integrated, it's summer. In summer we do the integrated rocket test, where we test our all of our propulsion system, or the whole rocket basically, in the vertical configuration. Where also the flight computer is actuating all valves of the system, so that we are set for the competition. And that concludes the design circle. After that, we enter a more logistical phase, where we need to get our stuff to the competition, work out our procedures again, practice, do rehearsals and stuff. It's a really complex system, but usually we divided in sub phases, like design, testing, reiterating, testing again, and then integrated testing. But all of them are more or less floating, because sometimes some developments take longer than others. So there's not really the one way we figured out yet. But we definitely will try to figure out the best systematic way in the future.
We also have to determine all of our important parameters, like tank sizes, or what amount of thrust our engine should have. All of those things. We have a sophisticated congruent engineering tool in Python written. And with that tool, we basically optimize all of those parameters to arrive at the optimal tank sizes and so on, that then later determine what we actually design in detail. So this tool models all of those things in a like simplified manner, and then compares all of the different rockets that come out and does flight simulations with those. And then we see which of those rockets that we could design actually achieve the highest apogee.
Every subteam will have software and, let's say, programs that they require. For instance, when we talk about aerostructures, I think they use ANSYS, for instance. When it comes to maybe fluid mechanics, you need to have simulations done in CFD. So every subteam will have specific programs and software that they require for.
What is the experimental rocketry community in your country like?
Great question. I think there's actually a bunch of stuff going on there. We are obviously not the only ones that do rocketry in that sense. So I feel like besides or one can differ between two aspects. So the first one would be student groups that are associated with university, stuff like that, like we, for example. And then there is also just people who do this stuff in their free time. So they have these kind of build smaller model rockets and fly them in their free time whenever they want to. So from our perspective, we can obviously give more insights on the student teams that are there in Germany. There are just plenty. So I think I wouldn't be able to count them all actually, but there are probably more than 10 different student groups that work in the field of experimental rocketry. So we have for some problems we have fruitful exchange. If we, for example, write to each other and say, hey, you've designed this component already, can we maybe have a chat about how you did that, how you approach that, and then you also meet regularly on certain events. For example, if there are any space tech fairs in Germany or so, you try to be representative with your team, and then you meet other student groups there that also face the same problems and challenges. And then lastly, there's also like unification of student rocketry clubs, Germany-wide association, which is called Bundesverband Studentischer Raumfahrt. Lots of German terms, but this is let's say the unified representation towards politics, so we can actually shape the landscape of student developed rocketry in a certain way that favors us. So we are also a lot in touch with those other teams, so that we can create the best or boundary conditions for us to develop stuff and test stuff and have the opportunity to learn during studies.
How do you promote your team?
Okay, so let's say our main means of communication with the people that follow us or also the sponsors are Instagram, LinkedIn, and I mean YouTube, I'd say a little less soon. Yeah, exactly. Actually, stay tuned because there's some really cool stuff happening on YouTube soon. So yeah. Anyways, yeah, main tool, definitely Instagram. Instagram is probably the easiest tool because it requires less editing and less, let's say, long texts, picture descriptions. And especially when it comes to events at WARR, for instance, test campaigns or manufacturing phases, we always try to keep our followers up to date through Insta stories and also, posts and stuff. And then when it comes to, let's say, sponsors specifically, of course, through direct contact when we, let's say, have specific requirements or when we ask a specific company to sponsor us, or maybe when people have maybe direct contact, of course, that's also an option. But I would say, yeah, mainly Instagram and LinkedIn and soon YouTube. Don't forget, please. Exactly, live streams, true. And the thing is, it's sometimes difficult when the team is so big, it's very difficult to keep a good overview of everything that is happening. It's also kind of difficult to transmit or let's say to express how interesting the things are that we're doing here. Because taking a picture of, I don't know, something maybe doesn't really explain how complicated and difficult it was to actually manufacture it or design it. And so it's always tricky to get across what we do here, but we try our best.
What are your experiences at EuRoC and your plans for future?
The experience at EuRoC, first of all, were really great. I think we had a lot of fun. I think that was for me, it was one of the really important parts, that the team has fun at the competition, so that everybody enjoyed it. Although we haven't had much sleep and food, to put it like this, but yeah, it just made me really happy to see everyone having fun despite these odds, because everyone saw it as an adventure, I guess. So yeah, this was really cool to see, and my best experience at EuRoC, I think, was that all the other teams, student teams, were really open about their developments, and you could talk to them really openly about rocketry, and the exchange was really great. I enjoyed it, talking to the other teams. We definitely learned a lot from the other teams, maybe taking some simpler steps in some systems, and but we could also see that some of our systems were also really thought through. So you could, verify your development and compare yourself a little. But to be honest, I think it didn't, most of the time, or I think all of the time, it didn't really feel like a competition. For me, it was just like being able to launch our system, present our system, but it never felt like we have to really compete against each other. I think it was a good shared effort in this sense. And goals for next year. So our plans are to get the operational part of launching a rocket more efficient, to be able to have an earlier launch window, so that it won't get as tight as this year again, because we were at the last moment where we were able to launch. Actually, I think they even extended the launch window for us on Sunday. So we try to be ready much sooner this time. Improve our operational aspects, get more efficient in that sense, meaning we want to practice more here at campus. Not that we didn't practice, but we saw that time is running really, really tight at competition, and you need to deal with lots of unforeseen environments. For example, the space where we wanted to build up our launchway didn't look as we expected, so we had to rearrange some stuff, and this all costs time that you would need in other places. So this is something we can improve on. And one of the most important learnings we got from our system itself, so from the rocket, is that we want to get it more robust to those environmental conditions. Because let's face it, out on the military side was dirty. It rained a lot, and we saw some issues with that. Although the system performed quite good, even though it rained the whole day. But there's definitely room for improvement, and now that we know what awaits us at the competition, we can adapt easier to these environmental conditions. And as the last part, as I already pointed out in the beginning, we want to really push those industry standards. Get into more high-tech stuff. We already developed our own cryogenic valves. We want to do so in the future as well. Our philosophy is always, if we can't find a cheaper supplier for something like that, we will build it our own. So this worked out for the valve, for example, because cryogenic valves are extremely expensive, and building it was way cheaper. So we went down this road. That's how I experienced EuRoC.
Biggest challenges you faced while preparing for EuRoC?
Yeah, so definitely the biggest challenge was integration and testing with the integrated system. Yeah, we had a lot of delays in the development for the engine and for fluid system and structure and so on. So in the end, we didn't have much time left to test everything integrated. We didn't expect it to be that much of an issue as it was in the end. Because we had done our job regarding requirements and so on to make sure that every system is compatible. But then, we found a lot of issues during testing. Also, for example, we had issue with our propulsion system during the last test campaigns because our fluid system mass flow wasn't as expected. So the engine couldn't deliver the full thrust that we needed. And we had to do some last minute improvements and tweaks to make it work in the end. But this almost led to us not being able to achieve the thrust that we need. And we almost couldn't come to EuRoC with a rocket that could achieve like the required exit velocity from the launch rail. But fortunately, we made it work in the end, and we could still join and try to launch. But in the end, we then also faced again some issues that led to us not launching. But definitely those were the biggest problems we faced with integration and testing. And that's also the reason why we are now planning to invest a lot more time into that and switch earlier to testing, have backup plans if components are not finished in time. And right now it's looking really promising, but we will see in the summer when we get closer to the competition if this adds up in the end. We hope for the best this time.
Yeah, having mitigation plans if something goes wrong is I think also one of the most valuable lessons we learned. So now we are already planning into our timeline when we have decision dates. For example, if we are not able to build our own valve until end of March, we buy a COTS one, so an off-the-shelf version for that. So I think planning, organization, and the whole project management aspect has become really important after the competition, because there's a lot of stuff that can go wrong, and you should be able to cope with these. All in the face of not being unsafe in your operation, which also plays a really big part in our team in general, because we put a really high effort into safety standards, doing this by introducing safety protocols through procedures and so on. And as far as I know, we were also the one and only team that pressurized from a distance. So while our system was pressurized, basically every human was at least 800 meters away, which we would call no line of sight in this sense, because if something would have ruptured, no human damage would have been seen. So I think in this sense we try to while pushing the boundaries of getting better and getting to industry standards, we don't want to lose the sense for the safety of our own members, because in the end what counts is that we all get home well. And I think that's also a really great achievement of our team, and we are further promoting this in our team when new people come in and so on. So this is also we saw and verified in Europe, basically. Let's put it like this.
Like, safety is also a really high priority in the design of our system. So for example, of course, we have requirements for arming, for example, and usually it is required to have at least 2 steps involved in arming the rocket. And in most of our systems, we actually go above and beyond that, and we actually require 3 steps and 3 things to go wrong, 3 independent things, so that the rocket would be armed, even though we don't want it to be. And as far as I'm aware, we are also the only team who where the pyrotechnics are actually armed when the rocket leaves the launch pad. So the umbilical connector disconnects, and that is the event that is the last step in the arming chain that allows our pyrotechnics to fire. The recovery, obviously, not the igniter. That would be a non-starter. But just to again emphasize our focus on safety, it also translates into all areas of design and operations.
What are your goals for EuRoC 2024?
To win it, of course. I already touched on a lot of things regarding goals for EuRoC. So first goal would, of course, fly our system the first time. Of course, we also would love to win the whole competition prize, but I think, in my opinion, this is not always the most important thing that we can gain from the competition, because at least for me, it's more important that we stay true to our own project goals, and if the project goals don't meet the competition goals, then I don't care much about the prize in the end. Of course, we were extremely happy about winning the design award, and we are confident that we can come up with a system that is capable of winning this award again next year. And maybe by getting the rocket off the launch rail and getting those altitude points, we're not that far away from winning the whole competition. But we'll see about that. In the meantime, we are constantly improving our system and try to push our own and the rocket's boundaries. So this is, I think, the main goals we are aiming for in the next competition.
How do you see rocketry evolving in the future?
For us, on our scale, it's very important that we keep on pushing our technological level overall of the system design that we have towards industry standards. We've said that a bunch of times again now, but it's really important for us to say that we can develop this difficult technologies, so to say, and prepare our students for the time when they enter industry, so they already have hands-on knowledge in these systems. So, for example, a switch to a pump fed cycle is really essential, but it's also the part of us working with a high degree of carbon fiber in the system, because those lightweight structures will find their way in the aerospace sector, or will expand in the aerospace sector. Then we are also working on type 5 pressure vessels, for example, which is also gonna in the end optimize the mass of our system. So there's a bunch of technological developments going on in our team that we are trying to push to get in the rocket. And the competitions are always super important for that, because it gives us a framework of trying out these technologies and having again a framework of development. So we can say that from competition to competition, we want to improve our system and try to implement a new set of technologies that will eventually help us to design a rocket that is comparable to industry standards. So this is the direction that we want to go in, generally speaking, with rocketry, or with our student group.
We talked already a lot about what we want to implement in future designs, but I think it's already quite a deal what we implemented currently into the system. So for example, speaking of liquid oxygen as oxidizer is already a quite huge deal, because touching on safety regulations again with this medium is quite not that easy to handle during testing operations that we frequently do here at university. And also the engine itself being regeneratively cooled by our fuel. And also, what we discovered is that we are one of the few teams that are actually capable of producing our own carbon fiber parts and glass fiber parts. So we are also really, really happy about this, that we are able to optimize our carbon fiber skin segments and our nose cone itself in shape and material layup, basically. So we are constantly pushing on the carbon fiber development as well, making the structure even lighter. And we are also running a load-bearing skin in our rocket, which I haven't seen much in the competition so far. So normally, or usually, teams run a lot of internal load structures with an aero cover around the whole rocket. And we try to make it work without the internal structure to get rid of the extra weight, basically. Also all of the valve development that we are doing. And as Matthias already said, the Type 5 tank development is also a really huge deal we are currently aiming for. But we in rocketry, people are always speaking about the propulsion system and the fluid system itself, forgetting about the electronics. So maybe you can say a few words what you already produced here with your flight computer, because I don't understand much about it, but I know how impressive it is. That's why I want you to talk about it.
The decision to build our own flight computer was made in 2021. It took us about 2 years to arrive at what we flew at EuRoC. Before, we were using a commercial off-the-shelf part that I'm told was worth in the 5 digits somewhere, the lower 5 digits. There were lots of problems, and they basically couldn't get it to work. And at some point, it was just decided that we're going to do it ourselves. And then basically we went through 4 iterations, and we arrived at a working system that, I'm pretty confident that it would have flown at EuRoC. There were issues, but there are issues with it. But I think now the focus is to make it robust. So basically what it does, the primary flight computer, is it reads in values from sensors all over the rocket. It estimates the state of the rocket. It detects launch, apogee, fires recovery with pyrotechnics. And it also, of course, one of the most important tasks is it controls the valves on the rocket. So it actually controls the flow of oxygen and propellant. The software is what is basically the brain of the operation. And it sends down telemetry. We get a nice high-speed downlink of data from there, and also it does some local logging as a backup. And all of this has been developed by us students in the span of 2 years. I think it's a really impressive feat, and I'm really proud of my team of this development.
Besides studying.
And in some cases also working.
True.
How much of your rockets do you build yourself, and how much do you outsource to sponsors?
That's something we are also quite proud of, that we produce a lot of rocket parts ourselves. So from the outer shape of the rocket, most of the parts that you can see are related to aerostructures. Obviously, so everything you see on the outside of the rocket is produced by us here at university, by our own students. That's mostly carbon fiber parts, but also glass fiber parts from the outside. Inside we have aluminum connector rings that connect each segments. These were partly produced by ourselves, but due to the high number of rings we needed, we decided to have them made by a manufacturer in the end. But yeah, we produced some prototypes ourselves, and they work quite fine. I think we even used one in the rocket in the end. It was just the sheer amount of parts that we couldn't handle in this case. So yeah, we can do complicated CNC milled aluminum and also other material parts. We have I would say one really skilled member in the team that is doing most of our parts. Shout out to Andrea. I think you met him at the competition. He was the one that was milling a connector last minute on the back of our pickup truck with our own mill. Funnily enough, he was able at the competition to make a adapter part where we haven't even had the thread cutter with us. So he basically made his own thread cutter out of a screw. So yeah, that's his special skill, I would say, and we are really happy to have him in the team. And yeah, he's producing most of our parts in this sense. The only thing he's not involved in is the carbon fiber stuff yet, but he's touching on that right now. Also. You've seen maybe our chamber, our region chamber at the competition. Of course, after it comes out of the 3D printer, it needs to be post-processed, and it's Inconel. And everyone that knows about Inconel material properties knows that it's not that easy material to machine. That was no big deal for Andrea. He post-processed our chamber really accurately. We had sealing surfaces on there, and everything worked out fine after he processed them. Also, Inconel is no issue for us right now. Of course, there's some 3D printed parts in the rocket as well, but mostly some holding structures for some fluid components. And yeah, I think that's about it, about the manufacturing stuff. To put it like this, basically all or most of the parts that you can see are done by ourselves. Also, the whole electronics pick and place. We ordered the circuit boards and the raw components and put them together ourselves. So the hands-on learning opportunities in the team are quite huge. You can touch on various manufacturing tasks and expand your knowledge beyond the pure design of a part, but also dive deep into the manufacturing tasks themselves.
What software do you use to design the rocket engine?
We have a custom Python tool that optimizes all of the performance geometry parameters that we have. So things like our throat area and how our cooling channels are shaped exactly. All of the geometry is then designed by this tool. And in the end, we then have to do the detailed design of all of the components with the commercial software that is available. So in the past, we have used SolidWorks and from ANSYS all of the simulation. For this competition, we are switching to Siemens NX software. We now have Siemens as a sponsor and use all of the simulation tools that are provided from Siemens directly. Are really happy with the tools from Siemens and achieve good results. For example, with the CFD simulations and also structural FEM simulations. We do all of those now in Siemens software.
I think on the software perspective, maybe Bernard, you can talk a little bit also about the flight computer software, because I think it's really impressive also that we do all of this by ourselves.
In the electronics team, we actually have developed a great deal of software as well. So the obvious one is, of course, the firmware that runs directly on the flight computer. It runs on a real-time operating system and is capable of reading in all our sensor values, processing them, doing state estimation, and sending down the telemetry link, and also some like housekeeping and control tasks here and there. And but it doesn't end there. So that's the embedded software part. We also have our custom ground control software. So what you see on the monitors in mission control, it's called EXUI. It's based on an open source project by NASA. And it displays all of our telemetry data really nicely. It allows us to control the rocket very nicely. And it's connected to the flight computer either via a wired ground link or via the radio frequency telemetry link during flight. And then we have like a couple of miscellaneous tools as well. that we developed. And in terms of the type of software we use Altium Designer to design our PCBs, which is, as far as I'm aware, pretty much the industry standard. Really capable piece of kit. And for software development itself, we use everyone uses whatever they're comfortable with. And in the end, we have our tool chain that compiles the software down to what goes on the actual processor.
One more thing that maybe is interesting for other teams as well. We basically converged now to an approach where we aim to do more software testing, and also the versioning is very important. So we use a GitLab, but that's like really common in software development and also general file management. We are now moving more to testing the software already during development, like setting up robust software testing workflows. And I can only recommend that to every team because we noticed some reliability stuff with software, and also for our software that we use for engine design and so on. It's really bad if we design our cooling channels, for example, wrong, and push those to manufacturing. So it's important to have tests also in this regard and check that it really works in the end.
Could you talk about the recovery system?
We have no recovery system experts here, but I watched the guys putting it together a lot of times, and was present at various integrated campaigns. So I'm basically an expert. The recovery system is, I think, a really basic recovery system we are currently using. So what we do is basically we use a commercially off-the-shelf CO2 ejection system. It's called the Raptor system. We have it redundant in the rocket, in the sense that we use 2 cylinders, each with 1 CO2 cartridge. So the PFC, our primary flight computer, actually fires 4 channels at the same time because they have redundant E-matches in there as well. So each of the CO2 devices require 2 separate E-matches that are fired from the, I think it's the same pirate channel, right? But just 2 physical E-matches because they have a probability of failure. So we run a redundant ejection system in this sense. And what we do is we basically just pop off the nose cone on top of the rocket. But we make sure that the rocket, that the nose cone, doesn't fly anywhere, but it stays still attached to the rocket by a shock cord. And then we have the recovery system itself. So the parachutes, we have a drogue chute and a main chute. So the drogue chute slows the rocket down initially, and then at roughly 400 meters, our main parachute opens. But we, of course, can also change this, or adapt this to environmental conditions shortly before launch, because we flash our most recent version of the code prior to launch, and there we can include the opening times and the backup timers as well. So also the recovery system itself is closely linked to the flight computer itself, because the mechanical stuff of the recovery system is the one thing, but the actual trigger timings are the other thing, and that's what's really important, because your recovery system can be quite elaborate and really good, but if you fire it at the wrong time, it just will rip apart due to aerodynamics. So it's really an interconnected part there. Currently, we run a quite simple system in the recovery system, and we are most likely want to run it next year at the competition itself. We did some integrated testing with this recovery system already, where we built a mass simulator of the rocket that featured the same mass and moment of inertia as the rocket does, and we threw it out of a helicopter with both the drogue and the main chute to verify its function, but also to see if the simulated travel speeds match the actual physical real parachute gliding speeds. We might look into different recovery systems in the future, but they will most likely not be initially tested on NIXUS, on the NIXUS rocket, but we shortly introduced a second project called Project WASP that is developing or building a solid propelled rocket with COTS motors. They will fly at Spaceport America Cup most likely, and we decided that this is the vehicle where we want to test new recovery systems and where we want to expand our knowledge into stuff like, for example, side ejection or other fancy stuff where we might not need black powder as an initial ejection energetic source anymore, so that we can run our rocket black powder free in the end, for example.
What is the payload of your rocket?
The payload of our rockets, it's actually a great topic because I would say we are pretty proud on the payloads that we've been using so far, because in that sense we are cooperating with another team of WARR. So I mentioned in the beginning that we have the different teams in our student group, and one of them does these microgravity experiments, right? So we decided to kick off some kind of side project for them. We call it Rocket Labs. This is where they are actually manufacturing scientific payloads for us so that we can bring them to the competitions. So we don't just want to load like a dummy mass or something, but have an actual like a valuable payload on there that we can even produce within our student group. So what they have been doing so far, or as their major research subject, was the aging and degeneration of neurons for Alzheimer's disease. And they tried to, or Space Labs, the other WARR team, they tried to develop an experiment that would basically build on the stuff that they learned on their first mission, where they were able to fly an experiment to the ISS. So this was in April 2023, or March till April 2023, and when the experiment came back, then we decided basically to continue this mission as the payload of Project NIXUS when we went to EuRoC last year. So it's pretty cool that we can actually do our own payloads as well. And we want to continue this collaboration between the two teams for the future, because it's I think it's quite some unique thing between all the other student groups that are competing, because we actually do cover this aspect as well, and we are pretty proud of that. For example, with WESP, with the other team that Lewis just mentioned, we want to fly at SAC. They will also fly a payload of Space Labs, so this Rocket Labs cooperation, and then again NIXUS at EuRoC 2024, they will have a Space Labs payload again.
Do you know Kerbal Space Program?
Oh, well, I know it, but I actually didn't play, so...
I mean, this is really crazy because I kind of thought it was a joke. But there is this one module that I took, and it's called Intro to Space Design or something like that. I don't remember. The whole point of this module was to basically make a mission. So they gave us a mission objective about the satellite, and they told us we needed to calculate a bunch of stuff, such as the orbits, masses, find sensors, and all of that stuff. It was pretty interesting. And one of the things they told us during the central exercises was to actually use Kerbal Space Program to calculate the orbit. And like I thought it was really funny that university actually told us to use this program, to play Kerbal Space Program, to make something out of it.
Yeah, so it became like a thing of some professors that they mentioned Kerbal Space Program in their lectures, or I think it was an exercise actually in basics of spaceflight. That's the name of the lecture, and also the guy who makes the exercises. How do you call him? I don't know. Okay, yeah, the tutor. Thanks. He also said like, okay, if we want to get a good feeling of all the space missions, we should use Kerbal Space Program to get an intuitive feeling of stuff.
Does your team have a big announcement you would like to make?
I think we talked about the more short-term and mid-term goals a lot already. So for example, like the developments now for EuRoC 2024, we want to improve on the existing system. Then EuRoC 2025, we want to fly the pump fed cycle, which will bring a lot of different adaptations we have to make for the system, because it's not only strap some pumps on there, but you have to design the whole fluid system for this. You have to design the whole engine for this. You have to conduct multiple test campaigns, stuff like that. So I think for the long or short and midterm goals, we already talked about that. But in the long term, I think we have a bunch of goals that we want to achieve with both projects that are running right now. The first one would be staging. So not in NIXUS, but in Project WESP, they are currently working on staging mechanisms that they want to test fly and then bring to SAC in this year. And then besides the staging, we also want to try to build a Hpper prototype, so vertical takeoff, vertical landing vehicle, which will also again require new technology in our propulsion system, for example. Obviously, I think this is the dream for every rocketry team. We also want to fly to space, so we want to cross the Karman Line with one of our vehicles. And this is also a long-term goal of, let's say, our bi-liquid propulsion development. So ideally, we want to achieve that with a bi-liquid engine. But again, those are rather the long-term goals, and we have to see where the projects are going right now, and which kind of new technologies or everything will be able to make this happen for us. Because what we've also learned in the past from one of our projects, that it's important not to aim too high initially, and try to do these iterations step by step. So you actually keep the experience of launching operating systems, launching systems within the team, with these frequent opportunities that we have in the competition every year. Because besides the fun that all the competitions bring, it's also really good to keep the members trained in all these aspects, and not try to build a behemoth of a rocket that will eventually take too long to actually get to the pad. So we've had a little bit of experience with these kind of projects in the past in our association, and we realized that it's better to try to approach these ambitious goals step by step. So this is why we keep these for the long term.
Do you have any advice for young rocketeers?
Honestly, the biggest advice I can personally give to really follow your passion, because, you know, being passionate about space, I mean, I may be biased, of course, but I think it's super cool. Space gives you the opportunity to obviously explore the dimensions that are unexplored yet. And there's so much space for people to find new solutions. And, you know, I always think about the statement, go big or go home, and space in general, rockets really give you the chance to go big, because there's, especially now, I think there's so many countries that are starting to get more involved when it comes to space exploration. And I think this is really one of the best times to get involved and start finding, you know, just find your way in the industry, and be creative, have fun, of course, and stick to it, because it's really cool and you can learn so many things. I don't have any specific advice, honestly, other than, you know, just stick to it and do it and experiment.
I think maybe find something, like, depending on where you are, like in life and physically, find some kind of opportunity to actually do something practical. So like a student group, or maybe a job at a company or something like that. Yeah, because I think learning theory can only get you so far, and the sooner you can start to actually work with physical stuff, the better.
I think it's also about exploring a lot of different subjects, because in the beginning there's a lot of stuff. Mostly we see it on new people joining the team. They mostly are floating between the teams and don't really know where they want to help. So the first advice here would be to, like Greta said, just start with it. You need to start with something, and if it doesn't suit you, you can always switch. But I think what I experience, or what I like to do, is switching topics once in a while, because your learning curve flattens off quite fast. So if you are exploring a lot of topics, for example, fluid propulsion, etc., you can, in the beginning, you learn a lot of new stuff, and I think you can gain the best grasp of the subsystem rather fast. I'd say, of course, it takes some time, and you won't be a genius after investing 2 months into one topic, but at least you know the basics, and you can talk about it, and you can say your opinion about stuff. And I think really exploring different topics is quite valuable, because your learning curve is extremely steep in the beginning.
To actually approach things step by step, because there are certain topics in rocketry that are extremely difficult, and you can't really expect to understand everything from the beginning. I'm talking, for instance, about control engineering, or when it comes to electronics, for instance, like it's very, very complicated, very difficult topics. So, you know, just don't expect too much from yourself, in the sense that, okay, if you invest 2 months in trying to learn something or understanding something and you don't fully understand it, it's okay, I guess. It's very difficult, so take it step by step.
What are your favorite space movies or space YouTubers?
Space movie?
What is it?
Interstellar, I guess. I don't know.
Why would it?
I don't know, because it's so absurd. I don't know, I guess. Yeah, for me it's Interstellar.
Like a TV show. My predecessor, electronics team lead Antonio, actually recommended to me. Now I forgot the name. Sorry, Antonio. No, right. The Expanse. It's called The Expanse. It's really nice. It's on Amazon Prime.
Yeah,
It's super cool.
I've heard it's really accurate in the sense of physics.
Yeah, they do half of the journey they have to accelerate and half of the journey they have to decelerate.
Oh,
which
what
is,
series that gets it right?
yeah.
My favorite movie is actually Star Wars, for sure.
yeah.
We were thinking about Interstellar, but Star Wars now is fine. Okay. I don't know. I don't know if I have a favorite space movie, but I also like Interstellar and Star Wars, of course. But if it comes to YouTubers, I also really like some stuff. I like VPS Space because he's basically the resemblance of a lot of stuff we said in the last on the last question about just getting started on stuff, because he's the best example. He came from a background knowing nothing about rocketry, and he just is basically a self-taught engineer that just worked on stuff until the stuff worked. And I really love watching his videos about space. I think I never missed one.
Bicycles with
No, it's not him, but he's also cool. That's me when I'm old.
So I'm actually not too much of a Star Wars guy, I have to say. I watched all of the movies, but I'm not so much of an enthusiast in that regard. Yeah, it's a German classic space comedy. It's called Raumschiff Surprise. I think people will not get it if they don't speak German. But besides that, I love actually watching. I think it's a classic choice, but I love watching YouTube videos from Scott Manley, because the way that he analyzes things is in a very accurate sense most of the time. I enjoy that, and enjoy like thinking about stuff in detail again, because for sure, I don't know, you're watching a live stream, for example, of a SpaceX launch, and then you think, oh yeah, this and this happened, but then he's like looking at every frame of the video and be telling you
this was happening.
Yeah, this is how you actually analyze stuff in detail. I think that's quite impressive. So it's like the appreciation of detail that can also or that can inspire you to think about or how you approach certain problems, and how deep in detail you can dive into some resources that you have. Also, like when it comes to your own technical experience, if we do some tests, for example, in WARR, you can look at the data and be like, oh yeah, I probably know what's going on there. But then you say again, okay, maybe I should look into it more in detail and try to understand every single physical behavior that is going on there right now. So I think this is why I really enjoy watching his videos.
Yeah, I take the chance to shout out some smaller YouTubers here. Louis already mentioned BPS Space, which is really great. But there are also, when you go to YouTube, you can get to so many small channels that build really weird propulsion stuff or rockets in general, and you can see a lot of different approaches and sort of get an intuition to what works and what doesn't by just watching those YouTube clips. For example, there's also a funny channel that tries to build a rocket out of beer kegs. He's not done yet, and he hasn't uploaded much yet, but you can already see what he's trying to do, and I think it will be great to follow this. And also from the Friends of Amateur Rocketry, where we launched our cryosphere rocket. It's located in California in the Mojave Desert. They also have someone there. I unfortunately can't remember the name of the channel, but he... I think it was just his name. It was Derek Konkawa. You can look him up on YouTube, and he uploads basically all of the rocket launches that take place at this launch site. Yeah, including our launch. You can see a really great video about our launch there. And so you will see a lot of student teams launching there and presenting the rocket, and you can see all of the details. It's really great to have those resources.
What's your favorite space movie or YouTuber?
Well, space maybe would be for me hard to tell, but YouTuber definitely Tim Dodd, the everyday astronaut.
Good
So,
choice.
YouTubers, of course, our YouTube channel.
Oh.
Very great YouTubers, guys. Please.
Soon.
Do you have any questions for me?
That you've been to this SpaceX school, so I was wondering, how was your experience there? Is it really as great as it seems online?
Well, the fact is, I came a little bit late, and in the year that I was supposed to start going there, COVID happened, so I had to do it all online. And then it wasn't really at Astra anymore because Elon Musk basically left the school. and the professors started their own school. So it was a bit different than it would have been if I went earlier and would actually have done it by going down to the SpaceX campus.
The process in the school, it's really applying all of the stuff directly, right? So have you been directly programming and working on hardware and so on, or how does it work in the school? What's the difference?
So I would say that it was still mostly theoretical, but that could have mostly been because it was online, because it was a bit hard to like build a rocket online. And so it was mostly theoretical. The main difference between the SpaceX school and a normal school is probably just the level, how advanced are the stuff, are the things that were taught, and also the professors. They were probably better than the average professors.
Sounds awesome. Are you planning to study at TUM at some point, or?
I think there's a relatively high probability that I will go to TUM as university.
Awesome.
How much did this year's competition contribute to this decision?
A lot.
Okay.
I didn't really know much about TUM before.
Okay, yeah, that's really interesting. We're working on that one. For me it was also quite similar. Before I wanted to start study aerospace engineering, but in your bachelor's degree there are not many programs in Germany offered in aerospace. I think it was just Stuttgart back then, and now TUM joined in the bachelor's degree as well.
I was the first one.
And Greta was the first one. Oh god. No. No, but in general, like the normal mechanical engineering course offers also the possibility to select the courses that you want in aerospace. Of course, that's what I did in the end. But you had another question, right?
I actually was wondering, where do you learn all of your stuff? Because you seem to know quite a lot about rockets, and I was wondering, what's your main source of information?
Well, I learned lots of stuff at EuRoC, but probably most of this stuff I learned watching videos from, for example, BPS Space, Karman Line, Tim Dodd, and also Wikipedia.
Okay, fair. That's nice.
Reading lots and lots of Wikipedia.
Yeah, that's a great source. And maybe another thing, I just saw on your LinkedIn profile that I don't know if you still work for them, if it was actually a job or more of a collaboration with DoSoft, if I'm not mistaken. I don't know if you are allowed to share anything about that.
No, DoSoft, yeah, it's basically a collaboration. I do quite a bit of stuff with them.
And is it more like, did you work at your own place, or were you really collaborating with them, going to the company and doing stuff for them?
I did go to Slovenia to visit the headquarters for a week, but basically all the stuff I'm doing at a distance in my home.
Pretty cool.
Also because I have to go to school, unfortunately, so I can't really...
I'm curious whether you are also like doing some kind of hardware projects and stuff on your own right now. So I don't know, I'm not so up to date on your social media like Greta is, for example, but maybe you've shared some stuff there already. But I was just asking if you are also building like your own model rockets or stuff like that.
Yeah, so when I have some free time, I usually like to build something. Lately, I've been more into electronics than into rocketry, but I did some rocketry. Yeah, again, mostly electronics. A bit of high voltage, a bit of high current.
The safety stuff.
Yeah, I've recently built a big Tesla coil, which I'm trying and failing to make it work.
Well, I guess that's the process, right? You don't learn if you don't make mistakes. Cool. You can. I'm sure we'll find a spot in our electronics team for you once you come to TUM when you're curious about these things.
You're planning to come to EuRoC 2024, right?
If I get invited again, then I will surely go.
We'll meet you there, I guess.
I was just wondering, was last year the first year you were at EuRoC, or were you there before?
No, I've been a year before.
Oh, nice. Okay.
I also did.
So you're basically a veteran already.
Maybe.
Oh, really cool. I guess you have more experience than we have then. I mean, not as a participant, but at least from seeing and talking to all the teams.
One thing I noticed that in 2022, there was significantly less liquid rockets than in 2023. However, in 2022, more of them launched.
Maybe there's a correlation there.
Can't imagine what. So yeah, I think that's closely related to. I mean, I think EuRoC kind of is the equivalent to Spaceport America Cup in Europe. And the whole time frame they might have adapted to is also the Spaceport America time frame where a lot of solids launch. So I think maybe the whole infrastructure and time you had to prepare the liquid rockets need to be a little bit longer than for solid rockets, because on solid rockets you pretty much prepare everything in a tent, bring it to the launch pad and stick an igniter in there, and that's it. And on a liquid system it's much more delicate to fuel it and get it working. So I think it's closely related to the fueling process, which is why a lot of rockets didn't launch in the end, and of course the system complexity as well. Yeah.
Also, the reason why we are now focusing so hard on robustness of the system and testing it integrated beforehand, because we noticed, for example, from the team from Guards, they had a perfect flight and didn't have any issues as it seemed, and they basically launched their entire rocket before the competition just to make sure that everything would work at the competition. And this just shows that once the complexity of the rocket with biliquid propulsion and so on is getting so high, you need to do all of those things in order to be able to launch with this time constraints that you have at the competition. And unfortunately, we can't do a complete launch before the competition to get to the same level of preparedness, but we want to get as close as possible to make sure that we launch this time and don't have the same issues again.
Yeah, thank you for the opportunity. It was really nice to talk to you. I hope you could get some more detail about our team, about our projects and so on. During EuRoC, you also had the chance to talk to the people. Maybe we went a little bit more in depth on the future, what we are planning to do, what we are doing right now, and stuff like that. So in a few months, hopefully all of that will be done, and you can watch the complete rocket at the competition in EuRoC then.
Thank you for coming to the interview. See you again at EuRoC 2024.
Yes, for sure. To it.
Bye-bye.
Bye.
Bye.
See you.
See you.